This is the final project for Linearity 2, and this is Yichen.
And Seungin.
And here we're going to explore the gradient descent and use visualization to get a better intuitive understanding of the algorithm. Gradient descent is an optimization algorithm used for finding the minima of a function. In machine learning, due to the large amount of data to be analyzed, the parameters of the cost function usually cannot be solved analytically and must be searched with an optimization algorithm. This is where gradient descent usually becomes very useful in finding the solution. Because the algorithm is widely used in the field of machine learning, there exists multiple variations of the algorithm. In this report, we will reveal some of the popular variations of gradient descent that addresses different problems and challenges associated with the original algorithm. Vanilla gradient descent is the basic version of the gradient descent algorithm. Suppose for a function j, we want to find its minimum. The basic idea is that we start with an arbitrary value, then repeatedly make slight changes to the initial values towards the direction of the steepest descent, until we reach a minimum value. In other words, we will repeat equation 2 until convergence, where n alpha here is the learning rate. Sometimes, when the dataset is too huge, it becomes inefficient to compute the gradient of the entire dataset. And here, we can use stochastic gradient descent, or SGD, which takes a different approach by computing using a single sample. Suppose we have the same function j and we want to find its minimum. And SGD takes steps by performing updates on individual data samples, which reduces the redundancy. Though SGD typically results in a higher fluctuation in the optimization function, it is usually much faster, and the fluctuation sometimes helps the algorithm to escape from local minima. Adding the momentum is an important method that can accelerate the SGD in the relevant direction and dampens the oscillation when it's approaching the minimum, just as how momentum works in the actual physics world. It is also very effective in pushing the optimization function out of the local minima. For the implementation, we simply added a fraction b of the velocity from the previous time step to the current update. Beta is usually set to 0.9 to provide the necessary boost for the function. Adagrad is an algorithm that is suitable for dealing with sparse datasets. It adapts the learning rate of each update, performing smaller, bigger updates for more infrequent parameters. Here, we're going to set GTI to be the gradient of the objective function. The implementation of Adagrad takes the form of the equation shown here. Here, GT is the diagonal matrix with each diagonal element II as the sum of the squares of the gradients up to the time t. And epsilon is a small term of the order of 10 to the negative 8 that avoids division by zero error. The benefit of the algorithm is that it eliminates the need to manually tune the learning rate. However, it also has one clear weakness. As the accumulated sum of the square gradients keeps increasing, the learning rate of the algorithm is going to shrink gradually and eventually become so small that no additional knowledge can be learned. Ada delta. Ada delta is an extension of Adagrad that is targeting to reduce the aggressive decreasing learning rate. Instead of summing out the previously squared gradient, Adagrad takes a different path by recursively define a decaying average e to the e of g squared that modifies the learning rate. We can simply replace the diagonal matrix GT in Adagrad with the decaying average over the past square gradients. Here, epsilon is still the small smoothing factor that avoids the error of division by zero.
So now we've looked at enough about the background of its gradient descent algorithm. Now it's the time for us to explore the fun, interactive, and intuitive demo of our gradient descent simulation on actual surfaces on Earth. We are gonna run four different algorithms, which is the vanilla gradient descent, the Adagrad, the Ada delta, and the momentum gradient descent. So these four plots are different gradient descent algorithms starting from the highest point on Mount Everest. And as we can see in the vanilla graph, the gradient descent gets quickly stuck at a local minimum at roughly 5,500 meters above. And it is expected because vanilla gradient descent has no means of escaping local minimums. And in the Adagrad plot, we can see that it gets stuck at a local minimum, and it's same as the vanilla gradient, except that it converges to that local minimum way quicker. And in the eta delta plot, we can see that it actually gets as low as 100 meters above the sea level. And we can, at this point, say this has made mostly down to the ground level. And if we look at the momentum plot, it continues to move down towards the ground level until it actually reaches ground level. And as you will see in a later video, it actually does a much better job than eta delta of climbing down the mountains. Now it's time to show you the actual visualization of these gradient descent paths on Google Map. We are going to examine 3 different places, including Mount Everest, Mount Olympus, and Olin College of Engineering. So this is me running our simulation on Mount Everest, and as you can see, the blue ones, the vanilla gradient descent, and the black ones, Adagrad, and we can see that they both got stuck at local minimum. And the green one here is Ada delta, and the red one here is the momentum gradient descent. And we can see that the momentum gradient descent has actually made really far down, and it's moving towards the direction where the ocean is located. So it's doing the best in this scenario. This is the same simulation running on Mount Olympus, located in Washington. As we can see, the both vanilla gradient descent and the Adagrad descent got stuck in local minimas, but this time Ada delta made all the way down to the ocean. But we can see that it's way noisier than that of the momentum, which smoothly goes down to the ocean. Again, it's the same simulation that we are running, starting from Olin College of Engineering, and as expected, the vanilla one and the Adagrad got stuck at local minima relatively quickly compared to Eta delta, but Eta delta this time also got stuck at local minima and did not make all the way down to the ocean. But as expected, the momentum gradient descent made all the way through the ocean.
That sounds good.
In this report, we studied and compared 4 different variations of gradient descent. In the Google Map implementation, we found that vanilla gradient descent had trouble escaping local minima and had low performance speed. Adagrad showed a significant improvement in efficiency but decreasing learning rate. It got stuck at a global minimum as well. Eta delta and momentum both showed better overall performance. Eta delta reached low value faster but showed significant oscillation in the process. Gradient descent with momentum had smoother curve and performed well in escaping local minima, though it took longer than Eta delta to reach the minimum. Because some of these algorithms we choose are designed to handle situations with multiple parameters, they might not have been most suitable for traversing the Earth's surface. But we were still able to observe the character of each algorithm through our visualization and got a deeper understanding of the mathematical model behind them.